Nah, now I'm live. I guess. What the heck is going on here? Like seriously. So did I set correct stuff here now? Yes. Is this actually? Oh my God, he died. So welcome to this advertisement episode for lgl.sillyhoon.com. Let me retype it. LGL stands for Lasergurkenland.sillyhoon.com. Not com.com. It's a freely reachable, high available, planned to stay on for eternity Minecraft vanilla server where you can play for fucking free, and I still don't know how to make these machines. This is my fourth try of making this advertisement episode again. I didn't do it in a while, and it seems like I totally forgot how like the internet works. But I felt motivated to advertise the server again. As you can see, there's only 2 players online, so it desperately needs more advertisement that people actually play here. Oh, where am I? Am I in the corner that I wanted to be? Yes, this is the one. Yes, we still have a machine here. Okay, cool. But before I actually start playing, I should make sure that we have audio and video at the same time. It doesn't seem like it doesn't seem like, where am I even streaming to? Stream settings. Where is it? Like, where can I? Where is this? What am I doing here? Okay. How can one suck so hard? Oh, I'm live. Wait. It's how can one suck so hard? It's a different URL though. Wait. It's how can one suck so hard? Wait a minute. It's a different URL though. Wait. It's still the old description? No. Wait a minute. It's a different URL. Stop this echo. What the heck, mate? Why does it still show the old stuff? Okay. So, well, let's remove that shitty IP here. Okay. Whatever. Let's just. It's still the old. Let's just start, I guess. What a mess. Okay, I will now play back the video. If you're interested in the server, watch any other stream.
Okay, so my talk is about Rust for C++ developers. The idea here is to give C++ developers a jump start to the Rust programming language, comparing, contrasting the languages so that it's easier to kind of get into if you are a C++ developer or have some background in C++. So my name is Pavel. I'm a developer, trainer, author. I have some books that I've written. They're all available online. And like I always say, please buy them, they make me money. So please do that. I authored a few tools that are part of my GitHub.
I've seen that intro already. Wait. Yeah, I've seen that shit already.
But if it doesn't, then it won't. So we can't really know upfront what you expect in some of these templates. And so this is somewhat going to be mitigated in C++ 20.
Let me check the audio again.
This is somewhat going to be mitigated in C++ 20.
Let me check the audio again. Sounds about right. Okay.
But Rust already takes one step ahead to mitigate that and make this always safe. So that's some kind of introduction. The most, I think, difficult part in grabbing with Rust is the idea of the ownership model. This is the fundamental change. I think this is the kind of the challenge from when moving from C++ or trying to understand Rust based on what you know in C++. So in C++, you can have a single owner or a shared ownership via various types, such as a shared pointer. You can have a single owner with a unique pointer, but really, you're not enforced in any way. You can make mistakes. For example, you can pass a raw pointer to some function, and that function may decide that it's going to keep that pointer for later. which is of course a bad idea, because if you intended to share that pointer, you should have passed along a shared pointer, but the compiler cannot enforce that and you're left on your own. In Rust, you have a single owner model at the basis, and that's explicit. And we'll see that this is something that allows the Rust compiler to make sure we don't make mistakes.
Oh, come on.
Make sort of maybe silly mistakes, but they're not so silly when you have a very large system on your hands. And so from C++ point of view, the developer has to know what it's doing. That's always been the case. I'm not saying it's good or bad. I'm just saying this is the way it is. This is the expectation. The expectation from the C++ developer is to do the right thing. In Rust, the compiler is the one responsible for making sure we don't mess things up. And so we have something called the borrow checker in Rust, which is responsible to make sure that we don't do things in the wrong way. I'll show you a few examples in a moment. And so in C++, we have assignment and copy construction. And by default, when we assign one value to another, they're just being copied. The copy constructor or assignment operator is being called unless we have an R value on our hands or use the move function and stuff like that. In Rust, this is kind of the opposite. So the model is everything is first moved. So if you assign something, you move the ownership from one variable to another variable. And so the previous variable now has nothing. If you try to use it, it will not work. And I mean, the compiler will tell you that you can't do that because it's no longer the owner of the object. And so what you typically do, you borrow the reference to the object to do some stuff with it, and then kind of return it to the owner. So typically you're going to borrow references.
Wait, like
and
this?
of course, the borrow checker will make sure you're not making a mistake. For example, you cannot borrow something and outlive the something that you reference in. That can never happen. The compiler will make sure of that. In C++, it's your responsibility if you take a reference to something, so you will not use it after that something may already be dead. So, enough talk, let's see some code. So here's a very, very simple example. Here's a C++ example. So we have a vector v1 that's initialized with 3 values, nothing very spectacular there. And then I'm assigning that or copy constructing that to v2 and v3. And because v1 is an L value in terms of in C++ terms, then the copy constructor is going to be activated. And once we run this, what we get is really 3 distinct vectors. They have no connection to one another. Each one is independent. We have a deep copy going on here with these vectors. Each one can be developed further on its own. It's unconnected to the other vectors. If you try the same thing in Rust, this is what it looks like. And so in Rust, we declare variables using the let statement. By the way, you'll notice that in Rust, all the keywords are as short as possible. So function is fn, and let is very short. So Rust is really about keeping things short. And what we see here is that we're initializing v1 using a macro. In Rust, when you see the exclamation point, it means a macro. It's not the same as a C macro, don't worry about it. It's not some kind of copy-paste that the preprocessor does and then you're left to deal with the aftermath. It is something different, but for our purposes, it creates a vector with 3 numbers. Notice I didn't have to specify the type. Rust always, or at least does a lot of work to infer types automatically, but it is statically typed, so it's nothing like some variant or some JavaScript object that can grow. This is exactly a vec of I32, which is the 32-bit integer.
Something is wrong here.
And so now when we do something like let v2 equals v1, we actually transfer ownership from v1 to v2. So now v1 holds nothing. And then the third instruction, trying to move v1 to v3, will actually fail, but it will fail in compile time. And so we get this nice error from our Rust compiler. So notice, I mean, if you've ever done C++ development and you're using templates and you have a compilation error, good luck with that. So you're looking at the error and it's kind of maybe 200 characters long, and those braces, the triangular braces are all over the place. You're not sure what you have to do here. The Rust compiler is really different. I think that statement from the marketing slogan at the beginning is completely correct. So it says, hey, value moved here in line 17. Value used here after move. And so you're getting a very clear error message. And in many cases, the Rust compiler will also provide suggestions of how to fix that. And so really, I think I'm very happy with the Rust compiler because it really helps me to do the right thing. And so how can we fix that? So one way to do that is use a specific method on vec, which is called clone. And that's because vec implements a trait, or you can think of that as an interface or an attribute, which is called clone, which has a clone method, and it really just makes a copy of itself. And so now v2 is a completely independent copy of the vector. Same goes for v3, and then we get to the same place as the C++ code. This just to give you an idea of what the expectation in Rust code. So assignment is really moving. It's not copying unless you call a specific method, if, of course, that method exists. That's a very simple example to start with. So here's another simple example that shows you borrowing in action. So let's say I'm writing this function. So this is a function in Rust. You can see that functions are declared with the fn keyword. We give a function a name, and then the parameters are given in this way. There's a
Was it even a detector array? I don't know.
the variable name, colon, and the type. In this case, I'm using the standard type string. And this is returning nothing, so I can just go ahead and implement that function. Notice, by the way, that the curly brace is on the same line. This is Rust good style. Now, most people like the curly braces on the next line. So I hate it. So I love Rust because of that, at least. All the rest is just nonsense. But the curly braces are the most important thing. And so now I'm in my main function, and I want to call this function.
He pronounced
So I'm creating a
that joke
string
way too serious, man.
using the associated, that is, static method called from. And the reason I'm doing that, I'm not just providing the string using which we'll not get into. So I'm going to create a real dynamic string which I can even change later if I wanted to. And then I'm calling greet name.
Wait, can you even hear my desktop audio? Like if I mute my... What the heck? Why does it... I messed up my audio settings, didn't I? Audio... Desktop audio default. Built in... A high definition audio controller. What? I don't get it. Whatever. Fuck my life.
And because I'm passing a name to the method, I'm actually passing ownership. And so this code does not compile. Why? Because on the next line, I'm doing something with name. But name is gone, so it's now an empty, sort of pointing to nothing. There's nothing there. So the compiler
How long is
does
the
not
fucking night?
allow me to have this code. So it says, look, value moved here. And so you're trying to use it again here. you can't do that. That's against the rules. And so the solution to that is fairly simple, and just need to get used to that. And so here's what I need to do. The function greet is not going to get the object string, but a reference string, because I just want to do something with that string, and that's it. I'm not trying to store it anywhere. I'm just going to use that as an input parameter. And so in this case, the call to the greet function passes along a reference to the string. So I have to put that ampersand in the declaration of the function and in the call site where I'm calling the function. Then I can go ahead and use name just function. This is a simple example of borrowing a reference and using that temporarily. And the compiler will make sure that the lifetime of the reference is not outlive the lifetime of the object it is referencing. In this case, it's very simple to see, but there are some other cases which are much more complex. Let's see another example where we actually thank the compiler for not compiling our code. So here's some C++ code which looks fairly innocent. I'm creating a vector of string and then pushing a string in there. And then I look at that value in V0 and then just displaying that. Then I'm pushing another string and displaying the previous value again. So this looks innocent enough. But if you try to compile it, it compiles just fine. The compiler doesn't care about anything. If you try to run it, I try to run it in Visual Studio in this case. And this is what I got in a debug build. It says something bad has happened. There's an access violation. It's an error to get to a location which has the weird address DD with many Ds. Clearly, that's not a good idea. So if you look at the code, if you're a C++ developer and think a little bit, something here is problematic. And the problem is maybe not so easy to spot, even though we have only about 4 or 5 lines of code. And the problem is that the second push needed to increase the capacity of the vector, so it was relocated to another region in memory, and the existing strings were just copied there. And so the previous reference was now referencing an old data which wasn't longer there. It's just not there. And the compiler cannot really help me determine that this is problematic. I'm going to hit problems at runtime. Maybe not all the time. If by chance there was still room in that vector, the capacity was higher, and a reallocation was not needed, then that would work. But then I deploy the application, and in some case, after I'm adding more and more strings and using this kind of code, it will crash. So I'm going to debug these things, and this is no fun. It's better if the compiler can tell me up front, this is a bad idea. So if I try to do that in Rust, here's the sort of the equivalent code. I'm creating an empty vector. Notice the mute keyword. So in Rust, all variables are immutable by default, so we cannot mutate them, we cannot change them. If you do want to change something, you have to add the mute keyword. Again, everything is shortened as much as possible, which again gives the intent. You're opting in, saying, hey, I declare my intent to make changes to this object, which I think is better than the opposite. Most languages take the opposite stance. You can do anything with a variable, and then in C++ you have to stick a const in various locations to say, hey, I promise I'm not going to do any changes to that particular object. And so I have an empty vector here, and pushing hello, and then I'm taking a reference to V0 in exactly the same way as the C++ code and printing that value. And then I'm pushing another value and printing the previous value as well. So if we try to compile that, I get another compilation error that says, hey, you borrowed a reference here immutably, and then you changed something here. So you mutated something while you have an immutable reference to the object. That's exactly a data race. And because of that data race, the compiler says, hey, I'm not going to allow that. So the compiler is, of course, very conservative, because it may be the case that this vector also has more capacity in it, and maybe that actually will not crash in runtime. But the Rust compiler is not taking any chances. So it forces the developer to do things differently to make sure that 100% that nothing bad will happen. So of course that means, as always in programming, there's no free lunch, you can't really get everything. So you do need to do some things differently, even if you can guarantee that that vector will not need any reallocation in this simple scenario. And so I haven't provided a solution here yet, we'll discuss. Yeah. So it will not work in exactly the same way, because once you have a mutable reference, you cannot have any other references to the same thing, mutable or immutable. That's the basic idea. If you have only immutable references, you can have as many as you want, because they can just read the data. But once you have one mutable reference, that's it. You cannot have any other references in the same scope. That's the idea here. Okay, so here's again some brief comparison from terms known in C++ to stuff that are implemented in Rust. And so this model of borrowing may seem like perhaps a good idea, but it looks kind of limiting. Because how can I share an object between multiple elements, maybe multiple threads even? It's not good enough to have just a single owner, so we need something more. And so Rust provides this as part of its standard library. So for instance, in C++, we have unique pointer. Unique pointer is very simple, something that allows us to have a single owner to something that is allocated typically on a heap. And so Rust has an equivalent called box. So I can take anything, give it to box : new, and that would be stored on the heap. And so the box will kind of point to that something. But box is a bit easier to use than unique pointer because of a trait that Rust supports. You can actually access the T object implicitly without doing any special .get or something like this to get to the underlying pointer. So it's a bit easier to use because this is a very common thing to do. For shared pointer that C++ provides, the equivalent in Rust are RC. This is the single-threaded reference counter. And we have ARC, which is the atomic reference counter. So if you need to share an object between threads, you have to use ARC, and that implements certain traits that allow it safely to move from thread to thread. So these are kind of the terms that you can see here, which make things a little easier to
What
understand.
the fuck, man?
So references exist in C++, of course, and as we've seen in Rust, references imply borrowing. And the borrow checker will make sure stuff is done correctly. And so the default in C++ is non-const. If you want something to be const, you have to explicitly specify that. In Rust, this is exactly the opposite. Everything is immutable unless you specify a mute, using mute keyword, that you want something to change. So let's see something a little bit more complex, perhaps. And so let's say I want to do something like this. I want to calculate the number of prime numbers between some first and last number, and I want to do that with multiple threads. So I'm going to do a very simple chunking by giving each thread a range of numbers to work on, and they're going to work on that concurrently and then give me back, each one will give me its result, and I'll just kind of add the result up. So that's a very simple, relatively simple thing to do in a multi-threaded world. And so how would I do that in C++? So here's an example of how to do that. I have a simple isPrime function that just knows to calculate whether a number is prime or not. That's fairly straightforward. And here's the main function called calcprimes. And so calcprimes receive the number of threads and the range of numbers for which I would like things to work. And so the idea here is that I'm going to create several threads. Each thread is going to get a chunk, a from and a to work on, which I calculate here. And then it's going to run in a loop and check each one whether it's a prime number or not. And if it is a prime number, I'm going to push that into a vector I maintain here. Now, if you've done any, and then of course I have to wait for the threads to finish using the that if statement, it was simply not compiled. The compiler said, I can't do that. I can't just transfer ownership to a different thread at first, because there's no guarantee that thread is going to be alive while that vector is alive. Maybe the main thread will terminate before that, and then we're going to have a reference to something that is already gone. So the compiler will not let me make these silly mistakes. And so the fixed version looks something like this. My data is a new vector, but here I have a mutex that takes that data. So the mutex is the owner of my data in a sense. So the data is hidden behind the mutex. So if I want to get to the data, I have to actually tell the mutex lock. Lock means acquire the mutex, please give me reference to the actual data while the mutex is locked. And when that variable goes out of scope after I do a push operation, then the mutex is released. So this is the general idea. And at the end of this loop, I want to get to the actual value again. I have to do lock here to get to the actual vector back and then return the size of the vector, because the purpose of my function is just to return the count of primes and not the entire list in this case. And so, again, notice I don't have any return statement, just writing something, some expression without the semicolon. And so, when I compile it and it compiles fine, I am guaranteed, I am confident this code is bulletproof. So it's going to run correctly anywhere. Because again, the compiler is very conservative. Even if there is a tiny chance this could fail in some mysterious situation, it will not let me compile this code. Okay, so let's move on. Another thing I want to show you, which is interesting in Rust, are enumerations. So enumerations in C++ are fairly simple. It's just a set of values. You can specify the exact value, you can specify the size of that enumeration, whether that's 4 bytes or 2 bytes or 8 bytes and so on, but really there's not much to it. It's just a set of values. Now in Rust, enums are different. So they can be just like the C++ enums, that's not a problem. Here's the season enum that we've seen earlier in Rust style, which is practically the same. But enums can be more interesting. Here's an enum, which is a generic enum that works on 2 parameters called T and E here, that has 2 values which in themselves are really a family of values. So one of them is called OK with some object, and the other err with some other object. And so this is in fact one of the types in the Rust standard library which is used for reporting errors from functions. So the typical function that may fail should return result of something and something. So the first something is what happens if the method works correctly, what the type that is going to be returned. And the second something is a type of error. We should provide the error information in case something doesn't work correctly. And the actual return statement in that function are going to be OK something or error something. And so the calling code can look at that result, and there are in fact methods in enums. So enums can have methods, so it's easier to work with the result. So if maybe I want to look at the error, maybe I want to look at the result, maybe I don't care about the error because I'm pretty sure that's going to be fine, so I can use something like unwrap and just take the result, and so on. So it's a very rich thing to have. Another one which is very common is called option. Again, it's very common to have that as return type from functions, which is very similar to the C++ 17 optional type, which means either you have something or you have nothing. So if you have something, T will be the something, and the value is something, or you have nothing. So you get back the non-value from the enum. So here's a different example. Those of you who are old enough maybe are familiar with a language called Logo. Anyone programming Logo at some point in their lives? I did that in some point. And so in Logo there's that thing called the turtle. Until today I have no idea why it was called a turtle, because it was moving sometimes very fast. And it's very unlike turtles I've seen. But it is a turtle nonetheless. And so if I want to model that, for instance, here's one way I can do that. I can create an enum to specify what kind of commands this turtle can work with, what the things that it can do. So in C++, I would have to just have a set of values and then have some way, maybe some substructures that provide the actual data to some of the commands, maybe using a union. So here we get that for free. So I have a turtle command. Some of the commands here don't have any parameters, such as rotate right and rotate left. Some of them have parameters, such as forward and backwards, and even pen color can have another object that has three fields, R, G, and B, which are representing the RGB values of some color, for instance. And so here's how I can work with something like this. Let's see a turtle. So
well, anyways, I guess that's it for this stream. I totally lost motivation. But please play here. It's so much